Okay, so today we are going to discuss some important questions from electrostatics chapter, and the topic which we are going to discuss will be electric flux and electric potential. So let's start with the question number one. Consider the potential at the corner of a uniformly charged cube of dimension L to be directly proportional to rho L square, where rho is the volume charge density. What is the value of the ratio of potential at the center to the potential at the corner of the cube? So first of all, it says that the corner potential is directly proportional to rho L square. So suppose this is a cube of side length L. So potential of this corner will be written as directly proportional rho L square, right? Now we need to find the ratio, basically the ratio of potential at the center to the potential at the corner. So first of all, so we need to calculate the potential at the center, okay, and we know the potential at the corner. So what we'll do here, so here we'll use a symmetricity concept. Means like this is the corner of a small cube. So we'll try to convert this corner of a small cube into center of another cube. Getting my point? So how can we convert this corner into center? So by placing three more cubes on this same level, like this, and one cube will be this side, one cube will be this side. So there are four cubes, and these similar four cubes will come on top of it. Okay, so I'll draw one diagram. So after placing these all cubes, okay, we'll be getting another cube. Yes or no? So this, but this time this cube will be have a length 12. Yes or no? So we are trying to like make a closed surface kind of. Okay, like that. Yes. So how many cubes we have? How many cubes are there in this 12 side cube? So 8 cubes. Okay, 8 small cubes we have. So once we convert this small cube into this big cube, the corner, okay, this corner P point comes to the center of this bigger cube. And what is the potential at this P now? So we can say that VP, which is the center of the bigger cube now, the center of big cube. Okay, so VP will be equal to, so what we'll do, so potential is a scalar quantity. So so we'll add the potential of each cube. So 8 times rho L square. So VP is directly proportional to 8 rho L square, and rho L square is 8 times potential due to small cube. Okay, small cube. So this is the potential at the center basically, right? That's what we need to find. The potential at the center is 8 times V small cube. And now we need to find the corner. So potential at the corner now, so that we can say easily it is directly proportional to rho L square, and L is the side. So what is the, so this time this is another cube now, big cube we have. So can we write the potential at the corner? Let's say VCO, let's say. So VCO corner is equal, directly proportional to rho 12 whole square. Yes or no? It's directly proportional to rho L square, where L is the side. Now this time the side is 2L. So it will be rho 2L square. So this is the potential at the corner, directly proportional to 4 rho L square and 4 rho L. And what is rho L square? The corner is directly proportional to 4 times V small cube. Okay, so that's it. Here now we have a corner, we have a center, and we need to find the center to corner. So center to corner is equal to 8 times V small cube divided by 4 times small cube. So this one is cancelled. So now it is, so we have a 2:1. Okay, so the ratio is 2:1 and the option is D. So option D is correct. I hope you understood this one. Let's move to the next question now. Okay, this is the second question, which is based on the relation between potential and electric field. So potential is given phi equal to xy, x and y coordinate, which are the following. So we need to like basically find the electric field, right? So how can we find electric field from the potential? So minus del v by del x I cap minus del v by del y j cap. So electric field is minus, if we differentiate del v by del x. So this is the partial differentiation, right? So with respect to x, the differentiation will be y I cap minus x j cap. Now this is the electric field. Now if we plot it on the xy axis, so this is y and this is x. Now this is the resultant which makes theta angle. So tan theta, we can say it is x by y, from this triangle. So the option D is not correct. Electric field at 2, 2 is root 2, which is also not correct, because electric field at 2, 2 is minus 2 I cap minus 2 j cap. Okay, and if we calculate the magnitude, so it will come as 2 root 2. Right, so that is also wrong. Now we just need to the direction. The electric field at all the points on positive x-axis. So there is no electric field on the positive x-axis. So this is wrong. Electric field at all the points on positive y-axis. Yes, positive y-axis. What is the direction of electric field? So it will be minus I cap. Now if we fix that y coordinate, so what will have? Electric field is in this direction. Yes or no? In y direction, right? So is in negative x direction. So that is correct. Understood? So option B is correct. Okay, so hope you understood. Let's move to the next question. Okay, question number 3. If the potential at any region varies in xy plane, V is equal to AXY. So it is like again similar to that last question, but this time we need to draw the electric field lines. So first of all, you can see from this one the V equal to AXY. Okay, so we'll try to draw the equipotential surfaces, and then from there we can find the electric field line, because there's a property of electric field lines and potential surfaces. The electric field lines are perpendicular to the equipotential surface. So from here, like if V is constant, right, on equipotential surface V is constant, so Y is inversely proportional to X. That means the equipotential surfaces will be hyperbolic, this type. These are the equipotential surfaces, but we need to find the field pattern. So you can see here now, okay, now from this equipotential surface you draw, imagining the field lines. Okay, those must be perpendicular to it. So how can we draw these field lines? So we can see now the field lines. I'll just change the color. So field lines will be, see, just I'm drawing the lines which is perpendicular to these. Okay, so field lines will be like this. See, all these field lines are perpendicular to each other, perpendicular to the field surface. Okay, now if we talk about the arrows, so in the potential surfaces, y is inversely proportional to x. That means if x decreases, y should increase. So the line should be this one. Okay, then only like in all the potential surfaces we can draw. So x is, so in this arrow you can see here the x decreases and y increases. Okay, so the potential will increase, so it is increasing here. Now if we draw the direction of field line, so okay, just for that what I'll do here, like I'll V equal to AXY, right? So I'll keep one variable constant. Okay, so if I fix x equal to constant, let's say, so if x equal to constant, so how can I draw? So suppose if I draw one line, okay, this is like one vertical line. On this vertical line you can see there are 2 points. Okay, this line is basically intersecting the equipotential surface at 2 different points. Okay, which point will have a higher potential? Can you think and tell me? So if on this line that these 2 black points, okay, the y is constant. Okay, so sorry, x is constant. So whoever is having more y will be having more potential. So that means if I mark 2 points A and B, the potential at A will be greater than potential at B. And from the field lines and equipotential surface property, the relation between them, we say that the potential decreases in the direction of electric field. So that means A to B potential is decreasing. That means the direction of field lines will be downward, A to B side. Okay, so that is correct in this option C. the arrow is downward only. So option C is correct. You can check with the other lines also, the other arrows also, with the same concept. Okay. So hope you understood. Let's move to the next question. Okay, question number 4 is related to the Gauss law. Okay, in the Gauss law, we write E dot dA is equal to Q enclosed by epsilon naught, right? Where we know that Q enclosed is the charge inside the closed surface, and this Q enclosed, the flux we calculate, right? So only the enclosed charges produce the flux. Okay, so that means the flux, we can say in short, the flux depends upon Q enclosed. So if Q enclosed is there, flux will be there. If Q enclosed is 0, flux will be 0. But on the left hand side, we have electric field, which is the net electric field, okay, which can be produced by any of the charged particles, enclosed, inside and outside. Okay, so that we already know about this Gauss law. Now see the options. If Q1 and Q2 lie inside and out, okay, so there's a closed surface, Q1 is inside, Q2 is outside. If Q1 changes, both E and phi will change. So this is correct. If Q1 changes, the flux will change. Q1 is an enclosed charge, so flux will change, electric field will change. Electric field to change hona hi hai, like, because that charge is changing. Okay, B option. So this is correct, है ना? We need to choose the incorrect one. So this is correct. If Q2 changes, E will change, but phi will not change. So if Q2 changes, E will change, but phi will not change. This is also correct. So Q2 is the outside charge. So whatever is the value of Q2, we know the flux due to this closed surface, every time it will be 0. Okay, irrespective of the charge. But electric field, net electric field will change. Okay, this is also correct. Option C, if Q1 equal to 0 and Q2 is not equal to 0, then E is not equal to 0 and Q is equal to 0. So that is correct. As long as Q1 and Q2 are not equal to 0, the E electric field will not be equal to 0. But if enclosed charge is 0, the flux is 0. That is correct. If Q1 is not equal to 0, then flux will not be 0. And if Q2 equal to 0, the E is no. This is wrong. So E should not be equal to 0. Because Q1 is not equal to 0. So any of the charges present in the space, so electric field will be present. So that is why this option D is incorrect. And the answer of this question is option D. Okay. So let's move to the next question. Okay, question number 5. Point charge Q is placed at P00A. Okay, so this is the Q charge placed here. The electric flux through CAP, okay, due to the electric field of Q is 5 then. Okay, so here just to find the flux through this square face OACB, so we'll use the symmetricity here. What you can do is, like, so there's one surface, one face, assume 5 more faces, okay, just to make a cube. So when you will make a cube, this Q charge particle will come to the corner. Yes or no? So you just need to imagine this type. So when the Q charge will come to the corner, okay, so this is our, like, the bottom face. So due to this Q charge, what is the flux passing through this one? So this one we already know, it is Q by 8 epsilon naught. This Q by 8 epsilon naught is passing through only 3 faces, right? So because of one phase, so through one phase, the flux will be Q by 24 epsilon naught. And this phase is divided into 2 equal parts, right? So half flux will go. So through half phase, flux will be Q by 48 epsilon naught. So the answer is Q by 48 epsilon, but in the options you see that there's a less than greater than sign used, inequality. So we can say one thing, this CAB, okay, so we have to be more accurate, okay. If nothing is mentioned, so we normally like Q by 48 epsilon, but if we like compare it with the flux passing through OAB and OACB, so we can say that ACB phase is like far from this Q charge compared to OAB. So that's what we can say, that the flux passing through this CAB will be less than the flux passing through OAB. So flux CAB will be less than flux OAB. And the total flux passing through this whole surface is Q by 24 epsilon naught. So we'll have to divide this Q by 24 epsilon naught into two parts. Make sure that this is satisfied. So with this one, like we can say the flux passing through CAB will be less than Q by 48 epsilon naught. Yes or no? Because the surface is far from that point charge, so the line density will be less compared to line density on OAB phase. So CAB will be less than Q by 48 epsilon naught, and flux through OAB will be greater than Q by 48 epsilon naught. Okay, so hope you understood this one. Let's move to the next question. Or let's do the next question. Question number 6. A ring of radius R is made out of a thin wire of area of cross section A. The ring has a uniform charge Q distributed on it. The Q naught is placed at the center. Y is the Young's modulus. Okay, so first of all, you should know the formula of Young's modulus. So Y is equal to, we know, like it is known as a longitudinal stress by longitudinal strain. Is F by A by delta L by A. So F L by A delta L. So this is the Young's modulus formula here. Okay, and the force which is acting, okay, the force which is acting on this wire, okay, that will be the force has to be along the length. Okay, A is the cross section area and delta L and L. Delta L is the change in length and L is its original length. So first of all, here we can see that there's a ring, okay, which has a charge Q distributed on it. Okay, and there's a charge center, okay, Q naught is placed at the center. So now because of the repulsion between Q and Q naught, we can see that the ring will be stretched. Okay, so there will be some tension produced within the ring. So that tension which we have to calculate now, and the tension we know, like it will be acting along the length, okay, along the ring, along the length of the ring, right? So that means this tension will be our F. So to apply this force, this formula, we need to find the tension. So let's start calculating the tension. So I'll take an element of the ring, okay. The charge on this one is lambda, let's say, charge density. It makes angle, okay, theta here. Now the tension will be in this direction, right, along that line only, along the wire only, and there's a Q naught charge and there's dQ, let's say. So there will be a force, repulsive force in this direction, electrostatic force. Okay, now you can see here the tension which is acting in this direction, so there will be a component. So this angle is theta, this is 90, so this horizontal component, so this 90 minus theta, so this will be theta. So T cos theta will be cancelled out. We will have two components in this direction. Now at equilibrium we can say that Fe is equal to 2T sine theta. I hope you understood this one. The tension which we are calculating within the ring, that could be another question, ki how much tension will be produced within the ring. Okay, so tension we are going to calculate. Now electrostatic force is 1 by 4 pi epsilon naught into Q naught into dQ by R square is equal to 2 into T into sine theta. Okay, now here we'll have to make some approximation that the Q naught dQ can be written as lambda into dl. So dQ is lambda into dl and dl is r into 2 theta, right? The total angle is 2 theta. So dQ is lambda r 2 theta divided by r square, and then we have 1 by 4 pi epsilon naught 2t, and theta is again, theta is small here, so sin theta becomes theta. So 2 theta cancel, 1r cancelled. The tension which we are getting is lambda Q naught by 4 pi epsilon naught into r. And lambda we can put, lambda is linear charge density, which is Q by the length of the ring, which is 2 pi r. So 2 pi r multiplied by this one, so we will get 8 pi square r square epsilon naught. So this is the tension produced within the ring. Now we have tension here, we have force, so delta L is equal to, from this formula, delta L will be equal to tension into length upon AY. Now just put the value. So T, okay, tension is Q naught by 8 pi square R square epsilon naught into L by A into Y. Okay, now we need to find the delta L. Okay, so we know our relation that L is can be equal to 2 pi R. The length of the wire is equal to 2 pi R. So delta L by L, what is delta L by L? Is nothing but delta R by R. Yes or no? That we know that from the like relative change. So that's what we can write. So delta L by L is equal to delta R by R. So this L will come here. So delta L by L is equal to delta R by R is equal to Q naught by 8 pi square R square epsilon naught AY. 1 R is cancelled. So now we have the final answer. Q naught by 8 pi square R epsilon naught A into Y. Right. So this is our D option. Right. So hope you understood. The answer is D option. Okay, let's move to the next question now. Okay, question number 7. 3 infinitely long linear charges of charge density lambda and minus 2 lambda placed in space. A point in space is specified by its perpendicular distance r1, r2, r3 respectively from the linear charges. So let's say the electric field due to the infinite length charge is 2k lambda by r. So if I change this value r1, r2, r3, so we'll be getting that 3 different fields. So this is a general electric field, the E equal to 2k lambda by r. Now from this one, if we calculate the potential, because we need to find the relation, okay, the equation of the potential surface. So V is equal to, so what we can write, V is equal to integration E dot dr. Okay, so E dr basically. So V is equal to 2k lambda by r dr, and that integration is 2k lambda ln r. So this is the potential, okay, a generalized form of the potential 2k lambda ln r. Okay, now if I put the value, okay, so electric field will be equal to, okay, so the potential basically. Now V is equal to what we can write. So if I change the value R1, R2, R3, so the net potential at the particular point, okay, a point in space. So what is the net potential? So V1 plus V2 plus V3. Now we'll just put here, so V1 is 2k lambda ln R1 plus 2k lambda ln R2, and this next one is minus 2 lambda, so minus 4k lambda ln R3. Okay, that's what it is. Okay, there's one more thing which we need to write, the integration plus C, and integration constant. So plus C will also come here. Okay, now V is the potential, okay, and we need to find the equipotential surface. So V is again a constant, so this constant is cancelled. Potential is constant, so we just need to get a relation, okay, when the potential is constant. So from here, like 2k lambda will be common and will go to 0. Now we have the equation ln r1 plus ln r2 is equal to 2 times ln r3. So this can be done as ln r1 r2. If I use the ln property, ln r3 square, so r1 r2 by r3 square equal to constant. Okay, yeah, equal to 1. So that's what the relation we have, and this option A is correct here. Okay, so I hope you understood this question. Let's move to the next question. Question by it, the figure shows a non-conducting ring which has positive negative charge non-uniformly distributed on it such that the total charge is 0. The potential, okay, so just like theory question here, we just need to see the statements and then choose the correct option. The first option, potential to all the points on the axis will be 0, and that is correct, because the net potential which we write is kq by r square plus h square. So due to positive charge, the potential will be positive. Due to this negative charge, potential will be negative. If we calculate the net potential, net potential will be 0, because that both are like equal charge, right? Q plus, total charge is 0. So net potential will be 0. So option A is correct. Okay, let's see the other options also. Electric field at all the points on the axis will be 0. No, it's not correct. The electric field you know, the electric field basically depends upon the directions, right? So there will be a, like, the electric field will not be zero, because the positive charge will produce electric field in this direction, this one will produce in this direction, and will have a certain field in a particular direction. The direction of electric field at all points on the axis will be along the x-axis. That is also wrong. We can see here that electric field which is coming here, okay, is in this direction, somewhat perpendicular to the axis. If the ring is placed inside a uniform external electric field, then net torque and the force acting on the ring would be 0. So the fourth option says that the net torque and the force acting on it will be 0. So it is also wrong, because that net charge is present. Okay, the minus charge and plus charge both will be like experiencing a net force, and because of the net force there will be a net torque. So this option D is also not correct. So option A is correct. So hope you understood this question. Let's move to the next question. Question number 9 is based on the relation between potential and electric field. The electric line of force which curves along the circular arc, the magnitude of electric field intensity is same at all the points on this curve, equal to E. If potential at A is V, then potential. So the relation is V initial minus V final. If electric field is constant, so we write just E into A. Yeah, E dot A. Sorry, there's a flux, E dot R basically, right? So V initial minus V final equal to E dot R. So from A to B, so what I'll do here, so I'll move from A to B now. So VA minus VB is equal to, electric field is it's constant E only. Okay, and the displacement, so AB, right? So this AB we need to find here. So what we can do now, electric field, so AB, how can we find AB? So see here, this theta, so this is theta by 2, so R sine theta by 2, right? Basically this is R sine theta by 2, this is R sine theta by 2, so total is 2R sine theta by 2. So VA, which is V minus VB, is equal to E into 2R sine theta by 2, and theta is, like, we can assume it is a small, because can see the theta is very small here. Okay, so here theta will take as a small, and electric field will be coming E. If we take theta as small here, so it will become theta by 2, so ER into theta, so VB is equal to V minus ER theta. That is like, could be one approach. The potential at B is V minus. There could be one more approach, like if we consider the direction of electric field also, and I think that could be like a more appropriate way. Like this is, because the direction of electric field, you can see here it is changing. Okay, I took this E is the effective electric field, okay, which is like in the horizontal direction. But if you take electric field at each and every point with the directions, right? So like how we can do, so you can take like a small, like kind of interval, okay, like if we take alpha and this d theta, the electric field is this in this direction, right? Tangential. So there will be two components, one is this one is downward, right? So though now electric field which is in the tangential direction, so if we write the potential difference, okay, across this element, so dV is equal to, we'll write minus sign will come, right? Minus dV is equal to E into, let's say this is dl, right? Yes or no? So dl is the length of the arc, so which is moving from this point to this point, this point to this point, so in the direction of electric field. So E dl. Now dl can be written as R into d alpha. Yes or no? So minus dV is equal to, or this can be written as V, let's say, okay, let it be minus dV, E into R into d alpha. And what is the limit of d alpha? Is minus theta by 2 to plus theta by 2, right? So when we are writing this minus theta by 2 to plus theta by 2, means we are taking these 2 points. So this is our A and B. So minus dV can be written as VA minus VB is equal to E into R into theta by 2 minus of minus theta by 2 to plus theta by 2, so theta jayega. So now this is V. So VB will be V minus ER theta. So that is again like another approach, and I think like this could be a like more satisfactory approach. Okay, so that's it. So option B is the correct answer here. Clear? So hope you understood. Let's move to the next question. Question number 10. A cube is made from 6 thin insulating square faces, each square having sides D carrying a Q charge. Magnitude of electric field leaving the sixth face due to the electric field of other 5 faces is 5. And the magnitude of electricity force on each face of cube is F. Then so now we have a cube, okay, with 6 faces, right? Each face has a charge Q. So let's say if this is a face A, B, C, D which has charge Q. So because of this face, there will be electric flux passing through other 5 faces. So if we try to calculate like how much flux this how much flux is passing through the 5 faces due to this one face only. So that will be so when we make a closed surface, so we'll put one more cube here, and the flux passing through the 5 faces due to this will be Q by 2 epsilon. So this is the flux basically which is like passing in through the 5 faces due to one face. Now if we think in reverse, okay, how much flux is passing through this one face due to 5 faces? So it will be same. Yes or no? Because the phase area is fixed. So whatever flux can pass through this one phase, okay, and that is Q by 2 epsilon naught. So the same flux will, pass through this phase only. Like if I say this one thing, suppose that Q by 2 epsilon naught is the flux which is coming out, let's say, from this phase, from each and every point on this phase. So how much flux you can assume, you can think of that how much flux can this phase accommodate? Same only, no? Q by 2 epsilon naught. Because this Q by 2 epsilon is the flux coming out of this phase from each and every point. So how much flux can go into this phase at each and every point? Q by 2 epsilon naught. So it's a reverse process which you need to think. So flux only we have to calculate here, and that is Q by 2 epsilon. So option B is correct. Okay, and here like we have to calculate force also. So to find the force, so what we can do is we need to find the force on one phase, right? So what I can think as this moment, we know the flux, right? This is the flux here which is passing through this cube, this phase only. So from the Gauss law, we know the surface area also. So from the Gauss law, E into integration dA, which is d square, is equal to the Q enclosed in the flux basically, which is Q by 2 epsilon naught. So the electric field present on this phase is Q by 2 epsilon naught d square, and because of the electric field, what is the force on this phase? So Q is QE, Q square by 2 epsilon naught d square. So this does not match with any other option, so that's why C and D are not correct. But this is the force, right? So that is so answer of this question is B only. Correct? So let's move to the next question now. So there's a cube here, okay, whose side is A, 0.1 meter. So the cube has 6 faces. Out of the 6 faces, the 3 faces are at the origin. Okay, here, like that. So this is the diagram. We need to find the flux through the cube, okay, in presence of this electric field. So electric field H square I cap. So H square I cap and Y J cap. So now the faces, those are on the z-axis side, so flux will be 0. Now we just need to think about the faces, okay, through which the flux is not 0. So first phase which I can think of right now, A, B, C, D. So there is a flux through this A, B, C, D because the area vector for this phase will be in I cap direction and there is electric field in I cap direction. The H square, so that means that for this phase the H value is A, the electric field from this phase is A square I cap and area is A square. So flux through A, B, C, D is A to power 4, right, and A is 0.1, 10 to minus 1, so 10 to minus 4. Clear? Okay, unit will come in Newton meter square per coulomb. Okay, now there's another phase which you need to think is, let's C, D, E, F, this phase. Okay, its area vector is upward in y direction, as we have electric field in y direction, which is y j cap. So y coordinate for this face A, so A and A square is the area. So flux through C D E F is A cube, which is like 10 to the minus 3 Newton meter square per coulomb. Now net flux we can write is 10 to the minus 4 plus 10 to the minus 3, and just need to convert it in this form. So I can write 10 to the minus 4 plus 10 to the minus 4 into 10. So 10 to the minus 4 common to 1 plus 10. Okay, in the units of this one, 1 plus 10, if you compare it, so beta's value is 1. Okay, 10 plus 1, 10 plus beta, so 1 beta is 1. So option A is correct. Clear? So hope you understood. Let's move to the next question. Question number 12. Consider an electric field E vector equal to E naught H cap, where E naught is a constant, the flux through the shaded area due to this field. The shaded area is this one. Okay, the area which you can see here, okay, it is at some angle. The area vector for this one will be in this direction. So first of all, let's to find the area vector, we need to find the side. So this side is A, this side it will be root 2A, right? So the area vector, so what is the magnitude of area vector is root 2A square. Okay, so if we see the side view, okay, this side we have H, this side we have a Z, and that this is the surface. Its area vector will be this one. So we have to take the components, one is H direction, one is negative Z direction. This angle will be 45. So this A cos 45. And this area is only responsible to produce the flux because the electric field is also in this direction. Because of this area vector, this component, the flux will be 0. Now the flux passing through this one is E naught into A cos 45. Now what is A? Root 2A square into 1 by root 2. So cancel, the flux is equal to E naught A square. So option C is correct. Okay, so hope you understood. Let's move to the next question. Question number 13. An infinite uniformly charged sheet with surface charge density sigma cuts through a spherical Gaussian surface of radius r at a distance h from its center. Show the electric flux through the Gaussian surface. So to find the electric flux through this Gaussian surface, we need to find the charge enclosed. So this is the charge enclosed which we need to find. So when this spherical Gaussian surface cut, so you can see like the shape of this part will be a circle only, right? So there's a like if we cut a sphere, okay, like at any point, so we get a circular shape only. So we just need to find the radius of this circular face. So this is r, this is h, so this will be r square minus h square. So that means that circular face which we are getting is the radius is root over r square minus h square. So what is the area? Pi r square minus h square. Okay, now so in circular face the charge enclosed is equal to sigma into area. So sigma into pi r square minus h square, and what is the flux? So q by epsilon naught. So sigma into pi into r square minus h square divided by epsilon naught. So option D is correct here. Clear? Let's move to the next question now. Question number 14. A point charge plus q is positioned at the center of the base of the square pyramid as shown. The flux through one of the four identical upper faces of the pyramid. So first of all, like to find the flux through this entire pyramid is like we need to make this q charge as enclosed. So I'll assume one more pyramid, okay, on the other side. So once this q comes to the center of this shape here, okay, so there are two pyramids. One is the above, one is the below. So now this is a like closed surface we have, right? So flux through this whole closed surface is q by epsilon naught. Then flux through this one pyramid. The flux through this pyramid will be q by 2 epsilon naught. Now this flux is passing through only these four faces, the triangular faces. Okay, there are four triangular faces, and there is no flux passing through this face, right? Because like the charge is in the plane of this flux face. So flux through the whole pyramid is 2q by 2 epsilon naught. Then flux through the, and this is passing through the four faces. So flux through one face only, q by 8 epsilon naught. Okay, so that is the answer. So hope you understood. So option C is correct. Let's move to the next question. Question number 15. A line of charge extends along the x-axis whose linear charge density varies directly as x. So linear charge density varies directly as x. Imagine a spherical volume with its center located on the x-axis. So this is the spherical volume. Its center is on the x-axis, which is moving gradually along it. So it is moving in this direction. So that we need to find the flux through which the graph of flux versus x coordinate. So as you can see here, the lambda is directly proportional to h, right? So as we move in this direction, so lambda will increase. So if lambda increases, the enclosed charge will increase. If enclosed charge increases, the flux will increase. So flux is directly proportional to enclosed charge, and that is directly proportional to lambda is directly proportional to x. So flux is directly proportional to x here, so that means the option C, straight line, is the answer. So hope you it is clear. Let's move to the next question. Okay, question number 16. The electric field components are given: x component, y component, z component is 0, and we need to choose the correct option. So first of all, EH is equal to minus ky and EY is equal to kx. So we know that EH can be done as del v by del x minus del v by del x equal to minus ky, and minus del v by del y is equal to kx. So from here, del v by del x equal to ky, del v by del y is equal to minus kx. Now if we divide these two equations, so we'll get del y by del x. Okay, this by this we are doing del y by del x equal to first and second, so first divided by 2. Okay, so y minus y by x, del y by del x equal to minus y x. Okay, so now if we solve this one little bit, so we'll be getting x dy, del y plus y del x equal to 0. So this is like d of xy we can write is equal to 0. So that means like xy is equal to constant. See, a constant is what? The potential. So basically like we are getting the equipotential surfaces. So equipotential surfaces will be hyperbolic from here. So yeah, so we are getting equipotential surfaces. So here now we need to find the electric field. Okay, so that is like extra steps. Okay, we can find the equipotential surfaces also. Now to find the electric field lines, okay, what we can do is so direction, if we see the direction, electric field is in minus x direction is this one ky, and this direction is kx. The resultant will be this one, and let's say this angle is theta. So tan theta is equal to what we can say is this is Ey, right? So Ey by Ex is equal to minus x by y, correct? And Ey by Ex, okay, we can write as dy by dx, yes or no? So if I put dy by dx is equal to minus x by y, now if we solve it, we will get y dy minus x dx equal to 0. Right, now if we integrate it, okay, just to get a relation between y and x, so I'll do here. So it is y square dy by dx will be, okay, one more thing, the dy by dx will be negative because the slope has negative. So plus sign will come here. Okay, so y square by 2 plus x square, okay, by 2 equal to c. Constant will come, if we are integrating here. So y square plus x square equal to c dash. Now this is equation of a circle, right? So that means like when we talk about the electric field lines, so this will be a circle. When we talk about the equipotential surface, it will be hyperbolic. So I solved both the cases. Okay, equipotential surface and the electric field lines. So when the electropotential surface is like this, so electric field lines will be this in circular form. Now when the electric field lines are in the circular form, so we can say, so the first of all, the fourth option is correct. The lines of force are circles, because we are getting an equation of circles, and if they are in circles, so that means that will be non-conservative, right? Because in circles, so make a closed loop, and the closed loop, like, it will be non-conservative. Okay, so that's how it is. Okay, so I hope you understood this one. So second, fourth are correct. That means option A is correct. Let's move to the next question. Question number 17, a positive charge plus q, negative charge minus 2q are placed at some distance in free space. The resulting line of force should be sketched as in. So plus q and there's a minus 2q, the electric field lines will be coming out from q charge, will be going to the minus 2q charge. Okay, and there will be no equilibrium point we can see between these two lines. So option A is wrong. Out of these B, C, D, you see the arrow. So in the D option, you see the arrow is like this one. So that is also correct. Wrong. So plus Q, the line will be starting from the positive charge, okay, and terminating at minus 2Q charge. Now out of these two, only that middle shape is different. So we know, like, when the charge magnitude is increased, okay, number of field lines also increases, the density. So we can see here that near to minus 2q charge, the field density should be more than this plus q charge, okay, which is correct in the option B. Okay, so the option B is correct then. Okay, and q has that field lines are like separated. Okay, there are rarer field lines we have here, so that because that q charge has less magnitude. Okay, so option B is the correct option then. Clear? Let's move to the next question then. Question number 18, consider uniform electric field 3 into 10 to the power 3 I cap. What is the flux of this field through a square of 10 centimeters side length and normal to the plane makes alpha, beta, gamma from the x-axis? So from this angle we can find the angles. See, alpha, sin alpha is root 3 by 2, so alpha is 60 degree, beta is 60 degree, gamma is 45. Now electric field is in I cap direction, so we'll be concerned about this alpha only. So now that area vector, okay, so this is the surface, let's say, okay, let's suppose that this is x-axis, this is y, this is z. The area vector is somewhat like this, okay, this, so the area vector will be like in this direction, okay, perpendicular to this. So it says that the normal to the plane makes alpha. That means this area is the normal, right? So it makes alpha angle with the x-axis. This is the alpha angle. Okay, it makes beta angle with y and gamma angle with z axis. But we are concerned about the x direction because the electric field is in I cap direction. So that how much angle that area vector makes with x axis? Alpha. So the flux will be E A cos alpha, right? So that x component only we need to consider. Okay, if electric field is in y j cap direction, k cap direction, so we'll be taking like cos beta, cos gamma and all. So now flux through this one, E is 3 into 10 to power 3 into area is 10 centimeters, side length is 10, so 100 into 10 to power minus 4 into cos alpha, alpha is 60, 1 by 2. So it is 50, 150 into 10 to the power minus 1, that means 50 Newton meter square per coulomb. So option B is correct. Okay, let's move to the next question. Question number 19, what is the flux through the part of the sphere x square plus y square plus z square? So this is a sphere equation, and we just need to find the flux passing through this first quadrant only. Okay, now it is a 3D shape, so just need to imagine. So first of all, like that this quadrant, okay, will be on the upper side. So there are two regions, upper region and lower region. This quadrant will be in the upper region. So first, let's say calculate the flux passing through this upper hemisphere. So it will be, we know, it will be q by 2 epsilon naught. Yes or no? So the whole is